So, good day again, students, and welcome to this nugget, which will concentrate on one specific aspect of the combustion process, namely the combustion temperature. You are all aware that a fire is hot, or to put it in another and stricter way, the fuel energy released during combustion will be found as heat energy in the combustion products, and the combustion products will have an elevated temperature. And then one important question becomes how hot these combustion products actually get, because that is what limits or facilitates the use of a specific fuel for a specific process. Suppose, for example, that you run a food manufacturing industry of some kind, maybe a bakery. Then you will be perfectly satisfied with temperatures below 300 degrees C. But if you run an electricity production factory, known as a power station, then you will want to raise the steam temperature to almost 600 degrees C. And if you run a factory where you recycle aluminium, you will want to have some 800-900 degrees C. This list can be made longer. So how can one compute the attainable temperature from a fuel? Let us look at a simple example. Pure ethanol is burnt at an excess air factor 1.2 using ambient air for the oxygen supply. Could this be used for the fining of glass at 1400 degrees C? As you see from the slide, does the mass balance not fit perfectly, and this is due to rounding errors. But now put up the equation for the energy balance. The incoming energy to the system may originate from the fuel, but in some cases the process may be run with preheated air. In the steel and glass industry, for example, air temperatures up to 1100 degrees are used. The adiabatic temperature is the theoretically highest reaction temperature. So to compute that, the assumption of no energy losses is made. Then all the incoming energy will ultimately be found as sensible energy in the combustion products. As with all thermodynamic equations of state, one is free to select a reference, in this case a reference temperature. Most common is to use 273 Kelvin or 0 degrees C. In our example, we also had that the energy in the air could be omitted. So the expression becomes simple enough, but what complicates things is that the Cp values for gases are generally strong functions of temperature. The diagram shows functional approximations for the Cp values for the actual gas components in joule per mole and degree, as a function of the temperature from 0 to 2500 degrees C. There are other functional approximations available, but I use these for temperatures above 0 degrees C and up to about 2000 degrees and at atmospheric pressure. In reality, a phenomenon called dissociation will occur at temperatures exceeding about 2000 degrees, but for this short course we will accept the use of these functions to 2500 degrees. Use the values in the slide to find that the maximum temperature in a well-insulated combustion chamber would be about 1750 to 1800 degrees C, which is more than 350 degrees higher than the required temperature for glass fining. So bioethanol could well be used as a fuel to produce container glass. When you do this type of estimates based on the adiabatic temperature, you must always have a margin. In this case, the margin is 370 degrees, so it is okay to say that ethanol may be used in this application. There is also another end to the adiabatic temperature. For a continuous and self-sustained combustion, there is a demand that the temperature is high enough. Again, the adiabatic temperature may serve as the first estimate, and one may say that if the adiabatic temperature drops towards 1000 degrees C, then it becomes questionable if combustion can occur at all. With biomass, which often contains significant amounts of water, may this sometimes be a problem. Let us now look at a case where the solid biomass is first converted to a gas and what happens then. What you do when you first convert a fuel into another fuel and then finally burn the converted fuel is that you split the combustion process in two. So let us do a very simplified example where we assume a fuel analysis and then just use simple stoichiometry to alter the state of the fuel from one assumed solid into an assumed gas. You will see the basics in the slide. The important thing is to remember that in a real conversion process there will always be a loss of energy. But in this example we neglect this and we assume that all the energy contained in the original solid is retained in the product gas. However, the energy is split into sensible energy, since the gas will be hot, and chemically bound energy. To be able to compute the flame temperatures using the computational aid you prepared before, you now have to calculate the ultimate analysis in percent by weight for the different gases. And then remember that if you want to store the gas or transport it, then you have to cool it down, or it will cool down by itself. And then the water will condense and you will get a dry gas. So consider 4 different cases and compute the flame temperatures. The original biomass is solid, so in that case you must assume an excess air factor about 1.2. For the 3 cases with a gas fuel, you may assume the air factor at unity. The values in this calculation are extremely simplified and may not be taken as correct, but they do illustrate that a conversion of a solid fuel into a gas, or indeed any conversion, does not necessarily mean that a fuel attains a higher quality. The usability of a fuel is set by a combination of factors, including the attainable temperature. Consider these things and then adapt a critical mind to how and in which cases a fuel conversion is really an upgrading of the fuel. And think about other aspects than the flame temperature. What about safety? What about transport economy? What about burner and combustion system complexity? What about corrosive fuel components? How will the price per energy unit be affected by a conversion? And so on and so forth.